Good morning, everyone. This is Sanvita, currently studying second semester of civil engineering in IIRE College. So today I am going to explain about homogeneous equations. So currently going to the introduction of homogeneous equations. Homogeneous equations form the backbone of linear algebra and differential equations, serving as fundamental building blocks across engineering, physics, and applied mathematics. So these special systems, characterized by their zero right-hand side, reveal deep structural properties that make them indispensable tools for modeling and analysis. So the power of uniformity, exploring homogeneous equations. So in our ODBC studies, we often look for patterns that simplify the complex world of calculus. So one of the most elegant pattern is found in homogeneous differential equations. As it is heart, homogeneity in the context means uniformity, whether we are looking at the first order equation or a higher order system. So these equations describe a state where every term works in same way, often balanced against zero. In our assignments, we typically encounter two types. First order equations where the variables stay at the same degree and linear equations where the source term is zero. Today, I want to demystify why these are the gateway to solving more complex real-world models. So the first order perspective, the y is equals to df strategy. The first order differential equation is a homogeneous if it can be written as a function of the ratio y by x. This means that if you scale both x and y by a factor lambda, the equation doesn't change. So the beauty of these equations is that they provide us with a reliable map for substitution by letting y is equals to yes. So we transform a non-separable equation into a separable one. So the substitution is more than just a trick. It is a way to simplify this relationship between variables so we can solve them using standard integration. And higher order stability, the auxiliary equations. As we move into higher order ODBC topics like second order linear equations, homogeneity takes on different meanings. So we look at the equations like ay double dash plus by dash plus cy is equals to 0. So here the 0 on the right side tells us we are looking at the natural response of a system, how a spring vibrates on a circuit case without external interference. So to solve this, we use the auxiliary or characteristics equation by turning calculus into algebra. We find roots that tell us if a system will oscillate like a wave or decay exponentially. So this homogeneous equation is essential foundation even when we move on to non-homogeneous problems. So we always find this part first. So, homogeneous equations are the building blocks of a vector calculus and differential model. They teach us that by recognizing symmetry and degree, we can turn a daunting derivative into a solvable problem. So as we tackle our ODBC assignments, remember that finding the homogeneous solution isn't just a step in the process, it's about finding the fundamental soul of the system that we are studying. Okay, so moving from introduction, why we care about homogeneous systems. So in engineering and scientific computation, homogeneous systems aren't just theoretical curiosities. They're practical necessities. Over 70% of engineering simulations, from finite element structural models to circuit network analysis, and network flow optimizations begins with homogeneous linear systems. These zero right-hand side equations provide a guaranteed baseline solution that anchors more complex analysis. So the homogeneous form acts as a mathematical foundation that ensures stability and predictability. So when you strip away external forcing terms, you reveal the intrinsic behavior of a system. Natural modes, the characteristic frequencies, the equilibrium states. The baseline understanding becomes essential when you later introduce universal disturbances and forcing functions. So from mechanical vibrations to electrical circuits to population dynamics, the homogeneous solution describes what happens when a system is left to its own device, making it crucial for stability analysis and control system design. So what is a homogeneous equation, first of all? Coming to linear algebra perspective, a system of equations expressed as in the form of ax plus b, where a is a coefficient of matrix and b is a variable factor and b is a zero vector. So every constant term equals 0, creating a system of balanced at equilibrium. And coming to differential equations view, for ordinary differential equations, homogeneity means no forcing term. A first order ODE takes the form fraction dy by dx, while the second order equation appears as a y double dash plus by dash plus cy is equal to 0. So describing systems evolving without external influence. So both perspectives shares a crucial feature that trivial solution always exists, but a real mathematical richness emerges when we ask, are there non-trivial solutions and what do they tell us about the system structure? So property 1 is the superposition principle. The sum of solutions remains a solution. So if there is two solutions to the homogeneous system and their sum is also a solution, this remarkable property means a solution set from the vector space. It's closed under addition. So to verify this algebraically, when we observe the linearity, A of V1 plus V2 is equals to AB1 plus AB2, which is equals to 0 plus 0, which is 0. The superposition principle is why homogeneous systems are so powerful. They allow us to build complex solutions from simple building blocks, combining fundamental modes to describe intricate behaviors. So this property fails spectacularly for non-homogeneous systems, making homogeneity a special and valuable condition. Property 2 is scalar multiplication invariance. Closed under scale. So for any scalar, lambda, if an equation solves A is equals to B, then lambda of B is also a solution. So this follows directly from linearity. A lambda by B is equals to lambda A by B. So lambda by B is equals to lambda just slash B. So coming to vector subspace section, it is combined with superposition, scalar multiplication as a solution that forms a vector subspace. A flat geometric object passing through the origin. So this subspace structure is why homogeneous systems are natural objects in linear algebra. So the vector subspace property transforms abstract algebra into geometric intuition. Solution spaces become lines, planes, or higher dimensional flats through the origin, making them amenable to visualization and dimensional analysis. This geometric perspective becomes crucial when we later study eigenvalues and eigenvectors. Key theorem. Undetermined systems yield infinite solutions. So the fundamental existence result. Theorem states if a homogeneous system has n variables and m equations, where n is greater than m, which means variables are greater than equations, then the system possesses infinitely many non-trivial solutions, which is beyond the trivial solution, 0. And here we have three stages: row reduction limit, free variables emerge, and parameterized solutions. Coming to row reduction limit, Gaussian elimination produces at most m, leading ones, periods, one per equation. And coming to free variables emerge, you have with n greater than m variables, at least n minus m, where one remains, where one variable remains unconstrained. And the third one is parameterized solutions. Coming to this, each free variable becomes a parameter, generating a continuous family of solutions. So why this matters actually? Any underdetermined physical model, more degrees of freedom than constraints, automatically contains a whole subspace of admissible states. So this flexibility is crucial for design optimization, control theory, and understanding system redundancy. In engineering terms, you have extra knobs to turn without breaking the fundamental constraints. So case study 1, solving a 4-variable 3-equation system. So adapted from standard linear algebra lecture materials demonstrating parametric solution representation. So coming to here, starting matrix. We have 1, minus 1, 0, 2, 0, 0, 0, 1, 6, 0, 0, 0, 0, 0, 0. So this system has been row reduced to its simplest form, revealing the pivot structure. Now we have to identify the variables. So leading variables are from the x row 1 and x row 3 correspond to pivot columns. So free variables are x dash 2 is equals to s and x dash 4 is equals to t and x dash 5 is equals to u. So these are the parameters that we can choose freely. And coming to parametric vector form, we have x is equals to s of 1, 1, 0, 0, 0 plus t of minus 2, 0, minus 6, 1, and 0, and plus u of minus 2, 0, 1, 0, 1. So the three basis vectors span the three-dimensional solution subspace. So this example demonstrates how row reducing system converts algebraic equations into geometric insight. So the three basis vectors represent pure modes of the system. Any solution can be expressed as their linear combination. So case 2 is a homogeneous system, which is, sorry. Yeah, case study 2 is homogeneous second order ODEs. So from Georgia text differential equations resources on linear systems, we have standard form, characteristic equation, and solution families. Coming to standard form, ay double dash plus by dash plus cy is equals to 0, which is a constant coefficient with no force in term. And coming to characteristic equation, we have a r dash 2 into p r plus c is equals to 0. We replace derivatives with powers. And solution families, three cases based on discriminant. So three distinct solution families. Case 1 is distinct real roots. When R1 and R2 discriminant positive, our y is equals to C1 ER1t plus C2 ER2t. This is the exponential growth or decay dominance. And coming to case 2, it is a repeated real root. When R-1 plus when R-1 is equals to R-2 is equals to R, which is a discriminant 0, where y is equals to C1 plus C2t of e power RB. So this is a polynomial exponential hybrid. And coming to case 3, it is complex conjugate. When r is equals to alpha and beta discriminant negative. So y is equals to e power of alpha t of C1 cos beta t plus C2 sin beta t. Oscillations with exponential envelope. So these solution families describe undamped springs, electrical LC circuits, and population oscillations. So everywhere the force in term is 0. The characteristics equation transforms differential calculus into algebra, revealing whether solutions grow, decay, or oscillate. And from chaos to clarity. So row reduction transforms messy, coupled equations into a clean, interpretable solution space. So what begins at an intimidating system of relationships become a transparent parametric description, revealing underlying vector subspace structure. So this process embodies mathematical elegance. Complex problems yield to systematic algorithms, revealing hidden simplicity. So the waterfall of row operations strips away redundancy, exposing the essential degrees of freedom that define the solution space. So takeaway and call to action. So universal scaffolding. Homogeneous systems are universal scaffolding for linear models. Mastering their structure unlocks every higher level application from network flow to vibration analysis to quantum mechanics. And design flexibility. As infinite solution spaces in undetermined systems provide engineers with flexibility for optimization, redundancy, and control. Understanding these solution subspaces is essential for robust design. The next step is to pick a real world model that you're working on, write its homogeneous code, and use the superposition principle to explore the full solution subspace. See how the abstract mathematics connects to your specific application. So whether you are analyzing structural stability, designing filters, or modeling population dynamics, the homogeneous solution reveals the system's natural behavior, the baseline around which all posed responses are measured. So this foundational understanding separates mechanical calculation from deep mathematical insight. Thank you.